We're gonna complete our discussion of this design.
She had a question.
When will they be due?
I don't know. Let's have them do tonight.
Right now.
Should have seen my look on your face. What's the last day of start? Friday or Thursday? Friday. Friday midnight mobile time. And by Monday noon, we'll have the comprehensive final posted available and feedback on all the assignments that you had previously handed in. And I believe I did fix it yesterday so that any of the quizzes that you've done, if you go to the My Grades thing and click on quiz again, it will tell you what the rating is for. The Monday after, I'm pretty sure we're all on vacation, right? So it will be available Monday and due Friday night. I hope we're all on vacation next week. I'm on vacation next week. All right, design. So today what I want to do, finish up design safety systems, talk more about that, and then go over the group 3 assignment, which we can do without logging into the Blackboard. It's just the submission thing we can't do without logging into the Blackboard. So we'll review that, and we'll talk about how that problem is set up so that we're all on the same page. It makes it easier for me to grade them because they all come back. I'd rather have them all come back and be perfect than have to sort through all the crap in this school. So, safety systems. We said safety systems are all around us, right? Maybe, yes. Right. Safety systems are all around us. They're there to protect us from so they're there to protect us from human error. They're there to protect us from ourselves and mistakes that we might make, and they're there to protect us from accident's a good word. They're there to protect us from perhaps equipment malfunctions, human error on our part, human error on somebody else's part, right? And these safety systems can consist of what are the kind of things that go into a safety system? Just quickly. Safety systems. What are safety systems? I'm pretty sure I know the answer. So, fail safe. So, all right. So that's. I didn't know about that, right? That's pretty cool. Good idea. So that's an internal system in the device that's protecting itself, right? That's fail safe. So you're talking about when you drop your phone in the water and shuts itself off. Oh, and so that's to keep it from being electrocuted. Oh, so it's got a fuse in it. Oh, okay. I was thinking of it would shut off the phone so that the phone doesn't get destroyed. Because maybe you get your phone away as long as it's not powered off. And as long as the water is really, really good. All right. So there was a fusible link in there. There's something that interrupts the power when it gets in the water. We don't electrocute ourselves by listening on the radio and stuff. Anybody listen to the radio and stuff anymore?
They don't use the tub anymore?
I mean, I might listen to music in the tub, but it's going to be coming from my cell phone, which will shut itself off when it falls in the water, based on my personal experience. All right, so I'm going to call it a fuse. What else could be in a safety system? Fine. Quickly. Guards. So physical guards, yeah. Please stop. Instructions. So procedures. Yep. You mean like eyeglasses, stuff like that? Yeah. So what's a sprinkler do? It was for fire protection. But it doesn't anticipate the hazard, right? It tries to make the hazard go away by developing it. So sprinkler, any other kind of fire protection system would be in a building fire protection system in that water. And so that's trying to mitigate the damage once the hazard has occurred. Many times that e-stop is mitigating the damage once the hazard has occurred, right? After you hear the machine crash, you press the e-stop so that it doesn't crash worse. Now you might also crash the e-stop because you think it's about to crash. It's a better time to press it. You typically don't set off the sprinkler system because you think there's about to be a fire. Although I suppose you could. This is why the insurance company doesn't want to reduce your rates. All right, so personal protective equipment. So it involves many things. Now, if we're going to stop. So how do we design a safety system? So we know the kinds of things that we can include in our safety system. How would we go about designing them? To understand what could go wrong. Understand the hazards. Hazard probably just want to see.
You could like look at the mistakes that people have made in the past.
Look at past experience. And so that's what we use our I wrote this in the API email list for, right? To gather data about past experience. So they hired this famous mathematician, statistician, back in World War II. And so what they were doing is they were looking at the bombers that were returning to Germany. And they wanted to make them safer because not all of them were returning to Germany. As they fly over there, not all of them come back. And so they wanted this guy to analyze the aircraft that returned and figure out where can we add armor to make them safer, make them more resistant to the incoming projectiles trying to shoot them out of the air. And so why don't we just add armor everywhere? That will weigh it down. Yeah, it makes it too heavy. Right, the military aircraft, fighter aircraft, they under-designed the landing gear. Because if the landing gear was over-designed, it would be too heavy, and then you wouldn't need it. Right, so they can't armor the whole thing. So he looked at the aircraft that came back, and he looked at where they had penetrations, because they would get shot but still come back, where they had penetrations from projectiles. And where did he decide to put the armor? Not necessarily, because they'd shoot up the aircraft and explode above them, like not necessarily below the plane. Where did he decide to put the armor? So there already was kind of armor around where they knew the crew was, because you can't fly back without the crew. Well, so what he did is he looked at the holes that were in the aircraft that were returning. And based on his analysis of where the holes in the aircraft that were returning was, he decided where to put the armor. Where did he decide to put the armor? Everywhere else. Because the ones that returned with holes in them didn't need armor in those places, obviously. They could fly with those holes. So he looked at the places that didn't have holes in them on the planes that returned. Kind of an interesting way to look at it. Because he was trying to figure out how do you protect how do you get the ones that didn't come back to come back? All right. So we look at past experience. We understand the hazards. If we're looking at And so once we sort of understand some past experience, we've done our survey, we've looked at our airplanes, we've collected our data, and we've got an understanding of the hazards. Now, what kind of hazards can hurt people? So we'll ignore hurting the equipment for now. What kind of hazards will hurt people? Quickly. In a machine shop, let's say. Yeah. We went through this on Tuesday. So sharp. Stop. Sharp stuff. What else? Yeah. So impact. What else? Hazards in a machine shop. Yep. Thermal. Electrical. This is the first one we're talking about. Let's go with sort of like so impact from sharp stuff or blunt stuff. Yeah. Stuff. Chemical. So high pressure air. The high pressure air. So OSHA actually has regulations about the air nozzles that they put on airlines in the workplaces. And they have to have vents on the side. So you can't just have an air hose with a nozzle that comes out. Does anybody know why that is? So if you were to plug the end of it, the air can escape out the side. Anybody know why that is? So you could make a projectile, but you can do that with the vents on the side too. In fact, that's one of the reasons that we require you to wear safety glasses even if you don't think anybody's working in the shop. Because there could be somebody right around the corner that's about to use air to blow chips off or something, right? You don't know, you can't see them there. But no, it's actually even worse than making a projectile. If you were to hold one of those air nozzles up to your skin and pull the trigger, it is possible at 120 psi to push an air bubble into a vein and kill you. Not likely, possible. That's why OSHA makes them have vents. Presumably. Every time I get a new generation of machine tool and I see new stickers that are more graphic and more informative on the hazard types, you got to realize that they probably have a lawsuit, and that's why there's a new sticker. They didn't tell me not to grab the spinning spindle. Therefore, I can sue them after I lose my hand because I grabbed the spinning spindle. So, all right. So we got these things. So, how are we going to protect ourselves from stuff flying apart, from impact, blunt force? How are we going to protect ourselves from those things? Yep. Good guards. The guards do what? They block it. Or so do they have to block it? Right? So if it's flying at you, do I have to stop it? They can slow it down so it doesn't hit you as hard. What else could they do? So you could arrange it so it's not possible for people to stand in the place where it would fly if it came apart.
Or if it doesn't fly, but just moves back.
Right. So the guards keep us from reaching into it also. So if it's coming out of energy, enough energy I have to make sure it doesn't hit you, right? Or take away some of the energy. So I doesn't have enough energy. They would catch it. All right. So, cards. To keep it go when it flies apart. How do we make sure that the operator doesn't with the guard? And so you may have never the mini mill when it was spinning. What happens? Stop. There is a setting. There's a version of that where it simply the operating program on those mini mills. If you open the door, it stops. There's an alarm that restarts the program. How are we going to protect ourselves from thermal in a machine shop? So we can guard against. How would we typically guard against a thermal energy? Keep your like that. Well, yeah, so we don't want the building to explode. But I was thinking, how do you keep the operator from being damaged by heat? So, personal protective equipment. If you're going to need to transport something that's hot, you use the special gloves.
Breathing.
Say again?
Breathing that allows to escape, but doesn't allow you to physically.
Oh, so a physical shield that keeps you back from it. Yeah. So we know, and so we have those in the lab. So you know how the servo motors stop the spindle so quickly when you hit the emergency stop? So that energy has to go somewhere, right? It doesn't just, you can't just shoot it off into space. That would be cool. But you can't just shoot it off into space. That energy has to go somewhere. We have to dissipate that energy. If you look on the top back of the mini mills or on the lathe in the lab, you'll see a heating coil in a stove. It's a giant resistor. And so what they do is and that has a guard on it so that you can't reach out and touch it. And so what they do is they put all the energy into that heating coil and it turns red hot and the spindle stops. That's how they do it. Kind of amazing. All right, so thermal energy, we keep us from getting too close to it. We interrupt the progress of it. Electrical energy. How do we protect ourselves from this? What's that? Protective equipment. You can also make it inherently safe. Make it so it doesn't have enough energy that it could hurt you. Make it so one of the hazards with electrical is when you get your flammables, they can sparks, cause ignition, cause fire. So you make it so it can't possibly cause a spark. For insulation. So the insulation is there to protect us on the electrical stuff. All right. So So you can go to their website. This is the National Society. The National Society for Professional Engineers. Anybody know the procedure to become a professional engineer? Well, you can actually take the test anytime. You don't have to have even gone to college to take the test. To the best of my knowledge. But there's a test. This society puts together the test questions. Depends on what type of engineer you are. There's a test for civil engineers, there's a test for mechanical engineers, there's a test for, there's a special test for engineers that are gonna work in especially cold environments. So there's a bunch of different tests. You take a test. Then you work for a professional engineer for something like 6 to 8 years. Then you take another test, and then you become a professional engineer. That's the basic procedure. If you have a master's degree, then the amount of time you have to work is shorter. If you have a PhD, the amount of time you have to work is shorter. You have to have done this test, worked with an engineer, done another test. Okay, so let's say you become a professional engineer. What does that get you? You're a professional engineer. Oh, you get more than just a piece of paper.
More money?
It could get you more money, because companies need professional engineers. They're willing to pay more for professional engineers. It gets a little stamp. Not like those embossed things like Registrar uses when they do your efficient transcript for everything. So you get a professional engineer seal. That's pretty cool.
You have to have a professional engineer license to start like a consultant.
Not necessarily. No, you can declare yourself a consultant and start a consulting company. Pretty sure today all you need is a web page. It does give you access to some higher level jobs. It gives you the ability to be sued. Because it gives you the ability to say that this is safe. And put your stamp on it. It allows you to be able to buy liabilities and emissions insurance because you're now able to be sued. Yep. I am not a professional engineer. Well, yeah, I prefer to be a professional manager than hire professional engineers. I'll still get sued. The company will get sued. But, no, I didn't want to take that test. Seems like a lot of work taking that test. My father's a professional engineer. My grandfather was a professional engineer. So I know a little bit about it. But the number one item in the code of ethics for professional engineers is to hold care about the safety and health and welfare of the public. And whether you're a professional engineer or not, this should be, as you're doing your design work, as you're doing your manufacturing work, this should be your number one ethical point. You can read the whole thing. It also says things like, so you get this PE stamp, you're a PE. Well, it doesn't say you're a professional engineer or mechanical engineering, it says you're a professional engineer. So in theory, you could now go stamp fire protection drawings, or you could go stamp electrical drawings, and it would be stamped by a professional engineer. In practice, you shouldn't do that unless you actually understand the stuff. So we started at the beginning yesterday. We talked about how doctors kill people. I know that the doctors tend to kill people one at a time, but engineers can kill people by the thousands. And we can do it on purpose by building bombs. We can do it on accident by designing things that are not safe. Not safe for a long time before anybody realizes that it was because of our design that it was killing people.
Like a bomb that.
Yeah. Yeah, the bombs that don't explode when they want them to are also bad. All right, group assignment 3. I'm very proud of group assignment 3. But in general, I tend to be very proud of everything I do. So you can see the text of the assignment by going to course material group assignment 3 here. Right next to it, group assignment 2. And so I had you guys. I give you a couple options. We either do the surface roughness or the food reflection one. You guys chose the food reflection one, what I remember. So I will admit I didn't go back and watch the video from that class to make sure that I remembered correctly. And so I've got here some data from an experiment that we completed a few years ago. It was actually part of that 1800 lab where the students collected the data. We have a tool that's made out of silicon carbide, SiC, and it has no coating. So just like the tools that we're using in lab right now. It had several different tool lengths. And so the tool length that we're talking about here is the overhang of how much the tool is sticking out of the tool holder. So all right, that should be right, because I didn't write anything yet. Good. So we have the machine tool spindle, right? Coming out of the machine tool spindle, we've got a tool holder with a tool coming out. So this is the length. It's the distance from the end of the tool holder to the tip of the tool. We've got the tool diameter. Yeah, I don't need to draw the picture for the tool diameter, right? You know what I mean there. Tool diameter, we have a spindle speed, 6,000 RPM. We have a workpiece material with 66.26 aluminum. So this is extruded. And we have measurements that were made. And so what was measured was the tool overhang. That's this. And the finished diameter of the workpiece after the operation was run. We're looking at a top-down view. We've got a round piece of stock material. We've got a tool that's going to come in, going to come over here, ramp onto the part, went around like this, ramped off the part, went away, went out. One single pass around. Program diameter. .8600 inches. Now, as we ran it, depending on how long the tool was, how long the tool overhang was, you'll see that we have different finish diameters on the part. Does that make sense? Intuitively, does this make sense to you? Okay. The data that's presented here is based on an average of 10 cuts for each of these diameters. So we prepared the tool, measured for each of these lengths, prepared the tool, measured the length, ran the program 10 times. This number here is an average of those 10 times. Okay, so there's statistical validity to these values. What I want you to do now, and so we've got some basic assumptions. We're going to assume that the workpiece does not deflect. In reality, we know that that's not true, right? We know that the workpiece and the tool both deflect. But to make the math easier, we're going to assume that the workpiece does not deflect. We're going to assume that the tool can be modeled as a cylinder. Now, in reality, the tool's not a cylinder, is it? So the tool will have some cylindrical shape here, and then it will have those helical flutes going around it. Right, so it's got less than full material down here where the flutes are. We're going to assume that it's a solid cylinder for our calculations. Okay? So we're going to neglect the fact that there's material removed in order for the chips to flow out of the flutes. We're going to assume that while it's doing this operation of cutting around, 100% of the cutting force is applied as a point load at the end of the tool. Now, in reality, so the tools like Yalon, and the force was applied along the bottom quarter inch of the tool. We're just going to assume that that whole force is applied at the bottom of the tool. Why are we going to do that? Makes the math easier, right? When we're doing these models, we want to make the math as easy as possible. All right, and we're going to assume that each, so this is 80 different iterations, right? For each of these, okay? So those are our assumptions, the basic assumptions that we're going to do. First thing I want you to do is plot I want you to determine from the literature to how much should the tool deflect? Anybody remember? Anybody remember the equation for deflection of a cantilever beam? What do you do if you don't remember the equation for the deflection of a cantilever beam? Yeah, so I'm going to say Google. Do that. I like doing this. And so you get the equation there. You can't really see it on the screen, but I-hands are deflection equals the force times the length cubed over 3 p I. What's I again? The area moment of inertia. How do you determine what I is? It's based on the shape, right? And so you can look that up. It's going to be based on which is why we said we're going to model this as a cylinder. If you tried to model it with all those spiral flutes, you would have a hard time determining what I is. All right, so we're going to model it as a cylinder. From the literature, you're going to find E. I tested this assumption. Took me 10 minutes. Standing in front of the computer. I think you can find E for silicon carbide, centric silicon carbide tool. What's the last thing we're going to do here? All right. So if we know length, I, and E, and D, deflection, we can calculate force. So you can solve that equation for force based on the data that was presented and assuming that all of the cuts had the same force. I want you to calculate the force. Now, to calculate that force, we have to assume that all of that cutting force was aligned in the direction of the deflector tool, right? Some of it wasn't, but we're going to assume that all of it was. And if you do that and present all of that, that's worth 60% of the assignment. It's fairly straightforward stuff. Look some stuff up in the book. Make a plot. Present a plot. Once you've done that, based on the workpiece material, 6061 T6 aluminum, and the force that you calculated up here, determine what the feed rate was for the operation. So remember, our power equals force times velocity, right? And it also equals, so that PC equals A times something times something times something. short of 1054 Machinery Handbook. So you can figure that out. So how do you have to, what's the factor that you're looking for? So you can look up the, so you're gonna have to make some assumptions, right? Because one of those factors is how sharp is the tool. Definitely one of those factors is how sharp is the tool. So they were all brand new tools. They were all used to make 10 cuts each. I would assume that it's a sharp tool. And that factor is 1, I think, right? Factor for a sharp tool is 1. So assume the tool's not dull, but list your assumption. All right, so you're going to do all that. And you're going to present your results in a written report. Do not exceed 4 pages. People say, what's the minimum length that it can be, right? I've given you a hard limit for maximum. I will stop reading at the end of 4 pages. Do not exceed 4 pages. The minimum length is as short as it can be to tell all the information. If you can fit all the information on 1 page and it's readable and I can understand it, 1 page is okay. I don't think you can quite do that with the graphs and whatnot. And in your report, list the given information from the top of the page, copy and paste. List the basic assumptions from the middle of the page, copy and paste. List any additional assumptions that you've made. Yes?
So the E value, is that also in the machinery handbook?
I didn't look for the machinery handbook, I used Google. 10 minutes. I had to read a paper that somebody published. Well, by read, I mean skim through it until I saw the graph that said it had modulus.
So, 1 paper per group.
1 paper per group, well, absolutely. Yeah, 3% of 4. Great. Whatever this number is. But everything clear? With your assignment? Any questions on your assignment? So, I believe I gave you enough information to solve all these things I asked you for. I haven't personally done the math yet to solve it myself. You may need to make further assumptions than the basic assumptions that I gave you. If you have to make further assumptions, simply list what they are. Okay? You won't all necessarily get the same force if you don't all find the same E. Correct? That's okay as long as the force you get lines up with the E that you got. Anything else? They would have been a huge day to remember to bring the first evaluation. I was thinking I put it off, I realized I didn't bring it with me. 4 times in a row I did bring it. I didn't have it. All right, so I guess they're coming on Tuesday. Tuesday's our last scheduled lecture. I will either Wednesday or Thursday. Since you guys come to class, you can plan which one it's going to be. I will hang out in the classroom during the scheduled hour for lecture to answer questions on the final project or anything you want to have questions about. Who wants to be Wednesday? Wait. Stand up if you care. All right. All right, so of the people who care, who wants to be Wednesday? 3. And the rest of you want Thursday? 1, 2, 3, 4, 5. Thursday it is. If it was Wednesday, though, you guys could just watch the video on Thursday. I like Thursday better. Anyway, this classroom is nicer than the other. The rules depressing. It was depressing? Why? Well, this one's got the windows, right? I think that other one's in the center of the building. It's like a bomb shelter, right?
Why did you ever go to that?
I believe that the people who schedule classrooms think I want to have class in that room, but it's not available on Tuesday and Thursday. So they find a different space for me to have class on Tuesday and Thursday. It's a reasonable assumption because it is about 100 people in my office. But I feel like the pressure is walking over here anyway. Uh,